A differential equation is any equation that involves a function and its various derivatives. Typically, at the beginning of this course, we're going to use the variable t for the independent variable and y for the dependent one. Everyone who's completed calculus has actually solved differential equations. An anti-differentiation problem is always an example. Suppose, for example, that we have dy dt equals t plus 1 over t plus cosine of t, and we want to solve for y. Well, we know that we can do so by simply computing the antiderivative. The antiderivative of t plus 1 over t plus cosine of t is t squared over 2 plus the natural log of the absolute value of 2 plus the sine of t plus an arbitrary constant. So you've all solved simple differential equations involving antiderivatives. In this class, we want to look at much more complex examples. Here's one. Dy dt equals minus 2 over t times y. Now again, t is the independent variable, y is the dependent one. We can rewrite this differential equation, dy dt, write it as y prime of t, and we can write y here as y of t. Typically what we'll do is we'll replace y of t with y. Perhaps it's out of laziness, but what we do is we say that we've actually suppressed the t here. So just bear in mind that this y is really dependent upon t. In some very simple situations, we can actually make an intelligent guess for what a solution might be. For example, let's take a look at dy dt equals y. We're looking for a function here with the property that y prime of t is equal to y of t. In other words, a function that equals its own derivative. The exponential function, y of t equals e to the t, is a pretty simple example if we reflect upon what we learned in Calculus 1. More generally, if we have 2e to the t, 3e to the t, 4e to the t, or any constant times e to the t, if we substitute it into each side here, it actually works. Maybe we could do something a little bit more involved, like dy dt equals 2 times y, or in other words, y prime of t equals 2 times y of t. With a few minutes of reflection, we can actually see that y of t equals an arbitrary constant times e to the 2t is a solution to this differential equation. Outside of a few simple examples like this, we really can't solve differential equations at this point. All we can really do is check solutions. So that's the purpose of the next few minutes. Here's a differential equation, dy dt equals 4 times 10 minus y. We'll actually see that this type of differential equation arises in the context of what's known as Newton's law of cooling. So it's a differential equation. It's an equation involving the derivative of some unknown function. And I'm going to tell you right off the bat that the solution is y of t equals 10 plus 3 e to the minus 4t. You'll learn how to get the solution pretty soon. Let's just check it at this point. The way we check is we substitute into each side of the equation. So for the left side, we take the derivative. The derivative of 10 plus 3 e to the minus 4t, the derivative of 10 would be 0, and the derivative of 3e to the minus 4t would be 3e to the minus 4t times minus 4 by the chain rule. And that simplifies to be minus 12e to the minus 4t. Now let's take this purported solution and plug it into the right side. So we'll have 4 times 10, and replace this y with 10 plus 3e to the minus 4t. Notice how the 10's cancel, and we'll have a minus 3, which when multiplied by a 4 is minus 12. So we get minus 12e to the minus 4t, which agrees with what we got when we substituted in the left side. So the solution actually checks. Here's another example. dy dt equals minus 2 over t times y. I'm going to tell you that y equals 1 over t squared, which is the same as t to the minus 2, is a solution. Let's substitute this into the left side. The derivative of t to the minus 2 is minus 2t to the negative third. which we can write as minus 2 over t to the third. On the other hand, if we substitute 1 over t squared in here, we get minus 2 over t times 1 over t squared, which is minus 2 over t to the third. This equals that, so both sides yield the same quantity. This solution checks. Another example. dy dt plus y equals e to the minus t. I'm going to tell you that a solution is t e to the minus t. Let's check. So we first have to compute the derivative. Using the product rule, the derivative of t e to the minus t would be 1 times e to the minus t plus t times the derivative of e to the minus t, which is e to the minus t times minus 1. That's by the chain rule. So let's substitute that in for dy dt. We have e to the minus t minus t e to the minus t. And then let's add on y, which is t e to the negative t. And notice how things cancel, so we in fact get e to the minus t, which is what we want on the right side. Here's an example involving second derivatives. We want a function with the property pardon the focus, a function with the property that if I take the second derivative of that function, I get minus 4 times that function. I'm going to tell you that y equals cosine of 2t is a solution. We'll check that. Now, in order to get the second derivative, we have to get the first derivative first. By the chain rule, the derivative of cosine of 2t is minus the sine of 2t times the derivative of 2t, which is 2. So I'm kind of doing this as a separate calculation. Now, to get the second derivative, I'm going to take the derivative of this. The derivative of sine is the cosine, so I'll have minus the cosine of 2t, this minus sign is coming down there, times the derivative of 2t, which is 2, times the derivative, this 2 here, which arose from the first derivative, which is 2. So I get minus cosine of 2t times 4, which is exactly the same thing I would get if I plugged cosine 2t in here, as I would get minus 4 times the cosine of 2t. So this solution actually checks. Here are some examples for you to do in preparation for class. dy dt equals 4 times the quantity 10 minus y. Y of t equals 10 plus 3 e to the minus 4t is a solution. This is actually the one we did just a few pages ago, so you can disregard this first example. Here's another one. dy dt plus 2y equals t e to the minus t. Please check that this is a solution. Y of t equals e to the minus 2t minus e to the minus t plus e to the minus t times t. Check it, just like I did on the previous pages. You're going to need to use the chain rule and the product rule in your calculations. Another example. The second derivative of y equals minus 16 times y. Show that y of t equals 3 sine 4t plus 2 cosine of 4t is a solution. You're going to have to use the second derivative, which means you'll need to take the derivative of this first before you take the second derivative. Lastly, the second derivative of y with respect to t equals 4y. Show that y of t equals e to the 2t plus e to the minus 2t is a solution. So please verify that for each of these, what I'm giving you for y of t is in fact a solution of the differential equation. And what I'd like you to do is I'd like for you to basically follow the format that I've been doing in this previous example.